who will be speaking to us via Zoom, as you can see on the screen, on the measurement problem, about which we've already heard quite a bit. I'll leave it with you, Osvaldo. Thank you.
Well, thank you. It's an honor and a pleasure to be here. Well, I'll start with a general introduction for those who are not familiar with the issue. So consider an experiment such as a wave that represents a single electron, which is a spherical wave indicated by psi, right? And as it enters a measurement apparatus, a Paulo chamber, at a certain point, an ionization takes place, and then there's a succession of ionizations, more or less in a straight line. But so this would indicate that we have a crepuscular phenomenon, and according to Bohr, it is a crepuscular phenomenon. But theory, quantum theory, especially the wave mechanics, represents the electron as a spherical wave, because that's the only way you can account for measurements involving interference. So if you consider this representation, you have a transition of a spread out wave that suddenly becomes collapsed, right? And so the measurement problem is basically the problem of understanding exactly what's going on. What causes this? Is it a stochastic process? Is it a deterministic process? So this process has its mysteries, and different interpretations have different views on it. So this is like the general measurement problem. I could give another example for those who are new to the subject. This is the Stern-Gerlach experiment. Now you have an atom, right? And after passing by the magnet, the atom is, at least that's what wave mechanics is representing. The atom is in two places at the same time, or has an amplitude divided into two. And then again, you measure the position of the atom, and you have a collapse. Since these detectors can be separated as far as you can put them, if you attribute reality to this wave, your conclusion is that this collapse is non-local, right? So this wave modifies its form in a speed that is faster than the speed of light, right? Okay, one didactical point here is that you might ask, why does the atom have to be represented with two amplitudes? Why can't we just suppose that it already chose the path after passing through the magnet? And of course, the answer is that we could have removed the detectors and recombined the beams, and in doing that, we would recover the initial atomic system, including its spin state. But if the system had already chosen which path it would take and the two possibilities of the magnet, that would not occur. In the end, the spin state would be different from the initial state. Okay, so that's just a general introduction for the newcomers. And in historical terms, we might ask, when did these problems appear for the first time? So an answer might be at the end of the 19th century, when research on X-rays were starting to develop. And J.J. Thomson noticed a curious phenomenon when he let X-rays into a gas detector. He had the hypothesis that the X-ray was a wave front, right? That was something still in discussion. But what he did observe experimentally was that photoionization occurred sparsely in localized points, right? And that called his attention. How could something spread out he detected in point-like manner. So Wheaton calls this the paradox of quantity. Later on, W.H. Bragg encountered a similar problem related to the energy of the X-ray. You can calculate the energy of the X-ray by the energy of the electrons that generate the X-ray impulse, and calculating the energy associated to the electrons, the final electrons that are in the gas that are ejected. Estimating the energies, they found that the energies of the associated to the whole X-ray impulse apparently was absorbed in a single by a single molecule of the gas. So not only was there something paradoxical concerning the localization of the object, but also the energy was localized and, in a certain sense, discretized. Okay, so that's the beginning of the wave-particle paradoxes. Then came old quantum mechanics, and finally, when the new quantum mechanics arose, it was Heisenberg who introduced the term reduction of the wave packet. And in the Soviet conference, he objects to a talk by Dirac, and just suggesting that it's not nature that makes a choice, but it's the observer himself that makes a choice. Because it is only at the moment when the observation is made, that the choice has become a physical reality, and the phase relationship in the waves, the power of interference is destroyed. So this is an important moment, because quantum mechanics apparently solves, roughly speaking, the wave-particle paradoxes by attributing to the measurement process an essential role, right? So this is something that it's part of the measurement problem. We'll see this as we go along. But of course, the general problem is, what is a measurement? What counts as a measurement? Is it the presence of an observer, a human observer, or... Okay, so when von Neumann comes by in 1932, he puts things in a more clear and formal way. And in this diagram here, I just want to represent the two types of evolution that he stresses. Unitary evolution is represented by the Schrödinger equation. It takes place in closed systems when no measurements are made, when there's no, when there's no noise from the environment. So this evolution in the initial phase here from T0 to T1 is, you can call it deterministic, in the sense that the initial state determines uniquely the final states, quantum states. It's reversible, linear, and continuous. Now, when finally a non-demolition measurement is made here, either in D3 or D4, this monophotonic state, or an equivalent electronic state, will lead to a single detection in one of the detectors, say D3. So at that point, the amplitude associated to path B disappears. And this transition is described by a different process, which was later called projection postulate, which is apparently indeterministic, reversible, nonlinear, and abrupt. But still, the question is, what exactly is breaking the unitarity of the evolution? Well, von Neumann just added a little, he added the measurement apparatus to the description and investigated whether this would solve things, but it really didn't, right? We would enter into a superposition of pointer states. This is well known, I'm not going to go into the details. He later on, in the same book, he proposed maybe if we could represent this measurement apparatus as a mixture of states, could that maybe solve the problem? And he had a criterion for considering that the problem is solved, and his conclusion was no, even in this general representation. We cannot explain the projection postulate only using unitary evolution, even if we consider very general quantum states, statistical states. So this is called an insolubility proof. Such insolubility proofs were investigated in the 1960s and 70s. I'm not going to talk about them. That's one of the meanings of the issue involving the measurement problem. So this first issue might be called mathematical, the completeness problem. Considering a closed composite system, can the projection postulate be replaced by the other quantum mechanical postulates, plus some adequate model of the measurement apparatus? And in exact terms, considering an isolated system from the environment, the mathematical answer is no. And the characterization problem, or more conceptual problem, is exactly under what conditions should one apply the projection postulate? And if it always follows a measurement, what is it that characterizes a measurement or an observation? Okay, so what I'm going to do now is mention 4 groups of solutions to this problem. And the first solution was the first one to have more impact in the popular literature, which is the subjectivist interpretations, represented here by London and Bauer's paper, according to which human consciousness causes the wave function collapse. So we're very familiar with this view. It's not very well accepted by physicists, but in a 2013 poll by Schlosshauer, Koffler, and Zeilinger, we can infer that around 6% of it was a conference on foundations of physics, and 6% espoused such views. So it's not a very popular view. And what they more or less, for us to understand what the claim is, let us consider the measurement apparatus involving various stages. The analysis would be when the beam is, Stern-Gerlach experiment, when the beam is separated. We've already seen that collapse does not occur here. But then there's interaction with for example, a metallic plate or a semiconductor, but before amplification. So maybe this interaction with a many-particle system could be sufficient for something similar to collapse to take place. Then after that, the electron that is ejected, superposition here, if no collapse occurred, we would consider that there would be 2 amplitudes of amplification. With this stage, when collapse occurs, an amplifier has to give energy to the system. This energy is not in any organized form. I mean, there's randomness involved, and so maybe that would be sufficient for making collapse occur. Then after a preamplification in the electronic system, finally we have a macroscopic registration. Irreversible, clearly the atom was registered on the top channel. And finally a human observer sees that and is aware of the result of the experiment. So the issue is, when does the collapse occur? Well, for the subjectivist interpretation, they imagine that not only the atom is in a superposition, but when it couples to the detectors become in a superposition together with the atoms, and then the macroscopic equipment as well gets entangled in this big superposition. And finally, when the human consciousness interacts with that, it is only then, with our freedom of choice, or some other reason, that the collapse takes place. So it is a far-fetched interpretation, but it is not subject to any empirical refutation, right? It is very old, so it's really close to the spirit of quantum mechanics, in the sense that it's been around for ever since the beginning of the theory. Okay, the second class of problems is the many worlds interpretations. In the poll that I mentioned, 18% of the physicists espouse this view. And the difference now is that not only the apparatuses in the environment get entangled, but also the observers, the human observers get entangled in such a way that collapse never really occurs, right? We've heard a lot about this in the conference. Now the third class of solutions, objectivist interpretations. I'm going to talk a little bit about these interpretations. They correspond more or less to 30% of the 2013 poll. And the basic program that I want to mention is the thermodynamic amplification program, but you also have objectivist interpretations coming from Bohm and de Broglie, and you can also associate objectivist tendencies and other classical interpretations. But let's focus on the thermodynamic amplification approach, which later on Bohr got, in the 50s he became close to this view. So the idea is that the crucial stage responsible for collapse is amplification. And what is amplification? Well, there's this metastable state, you have an external source of energy, and these can be described thermodynamically. So the strategy of these people was to use statistical mechanics according to different approaches, H theorem or more modern formulations, and try to describe what goes on in the measurement apparatus. And so this has been an ongoing program. It's never, I think, been extinguished. In the 60s, there was an argument that, in the philosophy community at least, was taken seriously. Tausk was the originator of this view, and it is related to the negative result experiments, which was proposed by Renninger in 1959. I should have brought a picture of the negative result experiment. It's basically a two-tiered experiment in which you can either measure here or here. And what you do is you remove one of the detectors, and now there's only one detector, and after a certain moment, when the atom should have passed, nothing is detected. So you can infer that the atom is in the other channel. So that corresponds to a collapse of the wave function. When Renninger proposed that as a critique of criticism of Copenhagen interpretation, the idea was that, well, in that case, we would consider this a corpuscular experiment, and if it's a corpuscular phenomenon, how can a particle that passes away from a detector be influenced by the presence of the detector? It's, they don't touch, so how can there be a collapse in that case? Anyway, so it's a good good discussion, and it was used against the idea that you have to have amplification to have collapse. So the point is, you can have collapse without amplification. So the answer to that is not far-fetched. I mean, Langer immediately responded, but there wasn't much of an impact in his answer. And later on, Dickey and others explored these types of experiments. But you can argue, if you picture things in a wave interpretation, the wave propagates and interacts with both detectors. And then when the collapse occurs, it might happen that the energy collapses to the other channel. So it's not that the quantum object does not interact with the detector. It does interact with the detector, especially if you consider that in some way the different amplitudes have reality, right? So of course this gets involved with interpretation issues, but so this was one of the thermodynamic amplification program. There have been other proposals that can be included as an objectivist approach. Let me just get one of these, Mashida and Namiki. What their proposal has different from the others is that they don't think amplification is necessary. They consider that before amplification, just with the interaction of the quantum object with the detection plates, that's sufficient for reduction to take place. And these issues are, there hasn't been, you can't really do interference experiments to try to single out whether, for example, the hypothesis that reduction occurs in the detection plates. I mean, you can imagine experiments in which you try to recombine the electrons that are ejected after the detection plates, but it's not a simple issue, and no one has come up with a decent experimental proposal in that direction. Okay, and the final group of solutions is basically that there's no measurement problem, or the measurement problem is not important, or it's trivial and it doesn't pertain to reality, it's only something involving our knowledge of the system. So this idea that a measurement problem is a pseudo problem, in the poll in 2013, more or less 27% of the physicists had that opinion. So this is something that is a new tendency, right? So the measurement problem, as a conclusion, has lost its popularity. I'll come back to that. Let me just mention a last idea, which is the idea of open systems, right? Which gave rise to the theory of decoherence. So decoherence more or less explores the same problems involved in the measurement problem, but it is a statistical approach. So it only, mathematically, it only analyzes ensembles, right? So it doesn't really answer the question of why a collapse occurs at this detector and not at another detector. But you have the notion of a decoherence time, which indicates that it's a time in which a collapse occurs. It only indicates that there's not really, as I said, a direct proof but many people believe that the decoherence approach offers a solution to the measurement problem, at least helps to understand the problem. Well, let me just pass on. So this is just a summary of the decoherence approach, the open systems approach. We all know it started in recent times with the Z, indicating that the environment has a role in introducing a decoherence into a system. So let me go back to the former slide. I should have skipped it. Imagine a scientist within a closed room. Okay, I think Everett might have formulated the problem in this way. And since he's doing a quantum experiment, collapses are taking place inside the room. But we're assuming that the room as a whole is completely isolated from the environment. So if quantum mechanics applies to macroscopic systems, we would expect that only unitary evolutions were taking place. So how can we reconcile these two issues? So with the idea of an open system now, we can say that no macroscopic system is really open, it's really closed. They're all open to fluctuations from the environment. Oh, thanks. And so this problem is solved. You can't really describe the macroscopic system as a pure state, right? And just comment that this is reminiscent of Burberry's 1896 proposal that external fluctuations account for molecular chaos, etc., etc. Okay, so the conclusions. First of all, the measurement problem is still open, or there's no consensual solution. One noteworthy tendency that we've seen is that there's a decline in the interest on the measurement problem, or attribution of importance to the problem. And this might be correlated with the rise of information theoretical approaches. And of course, the measurement problem hasn't had really much development. In the theoretical, well, we'll see there has been some, but nothing really definitive in terms of experiments, and theoretically things aren't developing very fast, so that might explain the situation. But what we do have in terms of experimental advances are various new paths, right? One of them involves the interferometry of molecules. So Marcus Arndt became well known with the interference of fullerenes, and he is one of his last works with his group in Vienna is the interference with. So he throws a molecule in a special diffraction grating, which is made of standing electromagnetic field, and the molecule he throws in is something as big as this. I just put the picture on because I wanted to show the symmetry. These molecules, the more symmetric they are, the easier it is for the effect to be measured. And so these molecules led to interference. So this is like the record breaking for molecules, interference of molecules, spatial interference of molecules. And from another path, we have these experiments with mechanical vibrations. So these are very exciting experimental systems in which you have macroscopic systems behaving as a quantum system. So these might lead to novelties in our measurement problem. And from the theoretical side, we have many works like this one here, which proposes a more detailed model of what measurement apparatus is, and then it goes on to, I was much impressed by, the different time scales for different processes, decoherence, dephasing. So this seems to be much advanced in the theoretical part as well. And experiments have been done, testing especially the stochastic reduction models, and have more or less selected some of them and discarded others. So all of this indicates that, the final question is, will the measurement problem be solved in our century? And I believe so, but let's stop here. Thanks.
Thanks very much. Okay, so we've got a couple of minutes for questions. Yep. Yes.
Okay, thank you.
Perhaps could I get you to come to the laptop? Sorry, just I know that's a hassle. And if I'll have a look if anyone else has got a hand. Sorry.
Hi, Weimer, what do you know me? You mentioned a decline of interest in the measurement problem, and I'm just wondering what your evidence is for that. Because as many people have mentioned, during the course of discussions, most physicists were not interested in foundational issues at all, and it was actively discouraged. So, what did you do, like a literature search, looking for certain phrases and found a decline in discussions, or what was that based on?
Well, that's a good question, and probably I'm not being very rigorous. It was based basically on the on the pole by Schlossauer, Koffler, and Zeilinger.
Well, if you're talking about the decline, then you have to have at least 2 temporal points, right?
No, you're right. No, I have the impression in the 60s there was much discussion on the issue. There were people proposing models, and there was the idea that the measurement problem is a real problem that can be either solved or described theoretically. And I got the impression that this this interest declined. But you're right. There's really not much evidence. I would have to go after that and do a more systematic research on that.
Thank you.
We got one more question, I think.
Yeah, thank you. Thank you for your talk. Just wanted to point out that actually, I mean, this is probably not yet material for historians, but like currently in the foundations of physics, discussion of the measurement problem are thriving actually since probably 2015 with rebooted Wigner-Strand scenarios and their extensions, and is actually very much active, and perhaps the topic should be analyzed also not only in the kind of standard old interpretational debate over the collapse per se, but also in these Wigner-Strand scenarios. That I think it's really so. At least as a note on the present and the future, it's actually growing the problem, but the battlefield has moved towards again the Wigner-Strand scenarios and their extensions. I don't know if you want to comment on something.
Great. No, thanks a lot. I guess, I mean, you guys convinced me, and I'll try to look over that again. And thanks a lot.
Okay, thanks.